right, folks. The position versus time plots of objects that are accelerating do not have a linear fit, and that's because those objects have have changing velocities. So again, we're going to be looking in this unit at objects whose velocities are changing, objects that are accelerating. If the objects are accelerating at a constant rate, the position versus time plot will have a quadratic fit. So last unit, all of our graphs were straight lines, right? We were looking at things with a linear fit. This unit, since we're looking at objects that are moving with constant acceleration, we should see them have a quadratic fit. So what do I mean by quadratic fit? Well, if you look, you can see the line is curved. Remember that parabolas are like U shapes, all right? So for this graph, the other half of the U would be in the negative time zone, so we don't really care about that half. You can see that if you extend it out to the negative part, that it does make a U shape. It does make a parabola. But that's how we know that this is quadratic. Also, when we do quadratic fits, we get pretty good fits, so that's another hint. Remember that quadratic graphs all follow the same general formula, and it looks kind of like this. So this is sort of like y equals mx plus b for quadratic graphs. This formula goes y equals ax squared plus bx plus c. And so then what we're going to do is we're going to turn this into a plot for position versus time, kind of like we did with the y equals mx plus b in the toy car lab. So which variable do you plot on the y-axis? Well, that would be position, right? We mark that with an x. Which variable do you plot on the x-axis? That would be time. We mark that with a t. And then what do a, b, and c represent in this equation? Well, a actually represents half of the acceleration. If you're wondering why it's half, well, I can't really give you a very good explanation, but it comes from calculus. So you're just going to have to remember that a is half the acceleration. B is your starting velocity. We'll represent that as a vi. Acceleration we're also going to represent with an a, so hopefully that doesn't become too confusing. And then for c, that's our starting position. And remember from last unit, we represented that with an xi. So I'll show you how that goes on the next slide here. So kind of in our first slot here, I want you to take the equation from the last slide, the y equals ax squared plus bx plus c. We're going to put that in right here, and that's going to be our general form. So y equals ax squared plus bx plus c. And then what we're going to do is just sort of start substituting in the variables from this lab. So next we're going to substitute time for the independent variable. So I'm going to write out that formula here. So you can see wherever there was an x, I put in a capital T for time. Next I'm going to substitute position for the dependent variable. Do that here. So instead of y, I've put down an x. So went from y to x. Next, I'm going to substitute the starting position for c. So remember, x is position. If I want to call it starting position, I put in xi. So instead of c, I've put in xi. Substitute starting velocity for b. So velocity is v. Starting velocity would be vi. Remember, the I stands for initial, so this is the initial position. This is the initial velocity. And then A is 1/2 of the acceleration. So I'm going to substitute in 1/2 of the acceleration for A. So how do you represent half acceleration? Well, it's actually 1/2 A. So this part might be the most confusing part. A becomes 1/2 A. This a is just generic. It means the number that comes before t squared. This a means acceleration. So whatever this number is, when you look at the formula for your toy car graph, it should be half of the rate of acceleration for the toy car as it's rolling down the ramp. Okay, so in this first example, we're going to use the graph and the best fit line information to write an equation for the motion of this object. So let's say this is your graph. This would be the equation x equals at squared plus bt plus c. And then they would give you something like a equals 0.5 meters per second, b equals 0 meters per second, c equals 0 meters. So we're going to take this information and write it into an equation. So we're going to start off the same way, x equals, and then instead of a, I've put in 0.5 meters per second, right down here. Instead of b, I've put in 0 meters per second. So instead of this b right here, I wrote 0 meters per second. And then instead of c, I put in 0 meters. So you can see down here, I've written in 0 meters. So hopefully that should make sense. We're taking this exact formula right here, but instead of a, b, and c, we're going to put in 0.5, 0, and 0 meters. And remember that these mean this is half of the acceleration, this is the initial velocity, and this is the initial position. Okay, so use the equation you wrote in example 1 to find the starting position for this object. So we're going to take that same equation, write it out right here. Now I'm going to find starting position. Well, remember, that's this third part right here, 0 meters. So now if I write it as a sentence, the object was at a position of 0 meters when the timer started. Okay? Let's do the same thing, but find the starting velocity. So we're going to take this same equation. This middle number is the starting velocity, 0 meters per second, right? Meters per second, those are our units for velocity. The object was moving at 0 meters per second when the timer started. So that tells us how fast the object was going when the timer started. We could also say that the object was not moving when the timer started, right? That would mean the same thing. 0 meters per second and not moving or resting or standing still, right? All mean the same thing. Okay, last up, use the equation you wrote in example 1 to find the acceleration of this object. So the equation is x equals 0.5 meters per second t squared plus 0 meters per second t plus 0 meters. So we're going to take this right here, but remember this equals half of the acceleration. So 1/2 a equals 0.5 meters per second. We'll multiply both sides by 2. A will equal 1 meter per second. So when you're using this equation to find the acceleration, you've essentially got to multiply this number by 2 to turn it into the actual acceleration. The way this formula is laid out is this coefficient here is actually half of the acceleration. Okay, and so then our answer is going to be the object is accelerating at 1 meter per second. All right, and so then the last thing we're going to do is we're going to interpret what this 1 meter per second means. And we're going to do that by writing a for every statement. So for every 1 second of time that has passed, the velocity of this object will increase by 1 meter per second. So if we go back to our last slide, we can see this 1 meter per second right here. That's telling us how much the velocity is increasing by. It's increasing by 1 meter per second every second. So at second 0, the object is moving at 0 meters per second. At second 1, it would be moving at 1 meter per second. At second 2, it would be moving at 2 meters per second. At second 3, it would be moving at 3 meters per second, right? So for each second of time that goes on, the object is moving faster by 1 meter per second. That's what we mean when we hear acceleration. Okay, and so then now you're going to take this, you're going to do the same thing with the data from the acceleration lab. You're going to go to Pivot, and you're going to get a screenshot of your graph again. This time, make sure you get the best fit information with there, right? So if you haven't done a quadratic fit to your data, you need to do that first and attach the data with a best fit line. And you're going to use the graph and the best fit information to find the average, no, not the average velocity. Well, hold on 1 second here. Let me fix this. Sorry about that. So you're going to use the graph and the best information, the best fit information to find the starting position, starting velocity, and acceleration of the toy car in the following questions. Um, so you'll paste your graph here along with the best fit information, and then you'll use the best fit information to write an equation for the car, and then you'll answer a few questions about the toy car, like tell me what its starting position, starting velocity, and acceleration was. If you have any questions, as always, let me know. Otherwise, I will see you all tomorrow.